In the vastness of the cosmos, where time has lasted for nearly 13.8 billion years, lies a mystery that challenges our understanding of existence. Our relationship with science fiction movies and ancient writings often leads us to imagine a dramatic apocalypse, a catastrophic end to everything. But what if the end of the universe mirrors its formation in ways we have never imagined? Join us as we explore the latest, most terrifying discovery from the James Webb Space Telescope. JWST. The universe has stopped expanding. This revelation, predicted years ago by renowned scientist Brian Cox, gives us the most realistic starting point for imagining the end of the world. Join us as we delve into the light that began its journey before galaxies existed, as we reveal the truth behind the halted expansion of the universe and the disturbing implications of Big Bang 2.0. Our ability to peer far into the cosmos allows us to see as far back as 13.8 billion years ago, near the Big Bang itself. Popular science and perhaps even the Bible hint at a tragic end, often imagining a grand apocalypse. But what if the end of the universe was no different than its creation? The James Webb Space Telescope, JWST, has revealed that the universe has stopped expanding, a prediction that renowned scientist Brian Cox made years ago. This discovery offers a new starting point for imagining the end of the world. JWST allows us to observe light that began its journey before galaxies came into being, giving us a glimpse of the oldest light in the universe. This is important evidence for those who still doubt the Big Bang theory. The evidence is visible in the light we can observe. The Big Bang is widely accepted as the beginning of our universe, despite other theories such as eternal inflation or the oscillating universe. The astronomical community largely agrees that the story of our universe and its history began with the Big Bang, an explosion that was much more than just an explosion. Starting from a point of infinite temperature and density, the universe rapidly expanded, and in just a second it was filled with protons, neutrons, electrons, and other particles. This expansion, often pictured as an explosion, is more accurately an inflation that stretches space faster than the speed of light. Our understanding of how the universe began is very theoretical, but technological advances have allowed us to explore these theories in greater depth. The cosmic microwave background, which scientists use to observe the echoes of the Big Bang, provides important evidence. However, it has limitations, such as not being able to see gravitational waves or residual radiation from the initial expansion. Despite these challenges, the Big Bang theory remains the cornerstone of cosmology. The Hubble Space Telescope was our primary tool for studying the expansion of the universe until JWST provided even more precise observations. The JWST images showed that the expansion of the universe had slowed significantly and may have even stopped. Light waves warped space and time, suggesting that space itself had stopped expanding. This discovery challenged our previous understanding that the universe was a sphere, with all of space and time enclosed within it. If the universe had indeed stopped expanding, this would point to a future collapse, a big crunch. This theory posits that gravity will eventually overcome the momentum of expansion, causing the universe to collapse into a singularity. This cyclical model suggests that our universe may undergo a series of expansions and contractions, potentially leading to new phases of cosmic evolution. The JWST data also prompt a reassessment of dark energy, which was once thought to be accelerating the expansion of the universe. If the expansion has stopped, then the role of dark energy must be reconsidered. This could lead to a deeper understanding of the fundamental forces that shape our universe and could reshape our entire cosmological model. The implications of this discovery extend beyond theoretical physics, affecting how we study cosmic phenomena and plan future space missions. Understanding the final state of the universe could provide insights into the behavior of celestial bodies under extreme conditions, influencing priorities for astronomical research and space exploration. In addition, the idea of a cyclical universe raises questions about the possibility of another Big Bang following the Big Crunch, suggesting that the end of our universe could be a transition to a new cosmic cycle. The JWST findings challenge our understanding of space-time, suggesting unanticipated behavior and potentially leading to breakthroughs in gravity, quantum mechanics, and the fundamental structure of the universe. In summary, the observations of the James Webb Space Telescope challenge our previous notions of the expansion of the universe and its ultimate fate. Scientists continue to analyze data and improve their models, which may allow us to uncover new insights into the nature of our universe. This ongoing research underscores the importance of curiosity and open-mindedness in our efforts to understand the universe and our place in it. As we learn more, the notion that the universe is not expanding will shake the foundations of cosmological research that have dominated for nearly a century. Edwin Hubble's discovery in 1929 of the expansion of the universe was a landmark event that changed our understanding of the universe. The redshift of distant galaxies showed that they were moving away from us, suggesting that space itself was expanding. This observation led to the Big Bang Theory, a concept that has been the foundation of cosmology ever since. The idea that the universe is not only expanding, but also accelerating its expansion, was further reinforced in 1998 when observations of distant supernovae showed that galaxies are moving away from each other faster than expected. This discovery introduced the concept of dark energy, an unknown form of energy that permeates all of space and is driving the rapid expansion of the universe. For decades, this framework has guided our understanding of the universe, leading to the development of complex models describing the evolution and fate of the universe. However, the findings of JWST challenge these long-held beliefs. Data suggesting that the expansion of the universe has slowed or even stopped represents a paradigm shift in cosmology. If true, it could imply that dark energy behaves differently than previously thought, or that there are other forces at play that we do not yet understand. The idea that the universe is spherical and that its expansion has stopped suggests a more complex and dynamic interplay of forces and energies than our current models account for. To fully understand the implications of this discovery, we need to delve deeper into the physics of the universe. The Big Bang Theory posits that the universe began as a singularity, a point of infinite density and temperature. As the universe expanded, it cooled, leading to the formation of elementary particles and eventually atoms. The cosmic microwave background, a remnant of the Big Bang, is a key piece of evidence supporting this theory. It provides a snapshot of the universe when it was just 380,000 years old, showing a nearly uniform light pattern with small fluctuations corresponding to the galactic particles and large-scale structures we see today. However, JWST's observations show that this picture is incomplete. The curvature of the light waves indicates a halt in expansion, implying that the structure and dynamics of the universe are more complex than a simple expansion model. This could mean that our understanding of gravity, space-time, and the fundamental forces will need to be rethought. For example, Einstein's general theory of relativity, which describes gravity as the curvature of space-time, may need adjustments to account for these new findings. In addition, the concept of a cyclic universe, in which the universe undergoes infinite cycles of expansion and contraction, takes on new relevance. This idea, which originated in ancient cosmology and has been explored by modern physics, suggests that the universe may eventually collapse into a singularity and then bounce back in another Big Bang. This cycle of birth, expansion, collapse, and rebirth could continue indefinitely. The JWST data may provide the first observational evidence in favor of this model, which has profound implications for our understanding of time, entropy, and the ultimate fate of the universe. Apart from these theoretical considerations, the practical implications of a non-expanding universe are enormous. For one thing, it affects our understanding of cosmic distances and the scale of the universe. If the universe is not expanding, then our redshift-based distance measurements will need to be reassessed. This could lead to revisions in our estimates of the size, age, and structure of the universe. It also has implications for our search for extraterrestrial life and habitable planets, because the dynamics of planetary systems and galaxies may be different in a non-expanding universe. In addition, stopping the expansion process could affect the behavior of black holes, neutron stars, and other exotic objects. For example, the formation and growth of supermassive black holes at the centers of galaxies could be affected by the lack of cosmic expansion. Similarly, the lifetimes of stars and the distribution of elements in the universe could be affected by these new dynamics. The findings of JWST also have philosophical and existential implications. The idea that the universe could end in a big crunch, collapsing back into a singularity, raises questions about the nature of existence and its cycles of creation and destruction. It challenges our understanding of time and linear progression from beginning to end. If the universe is indeed cyclical, then the concepts of birth and death, creation and destruction take on new meanings. This cyclical view of the universe echoes many ancient philosophies and religions, which view existence as an endless cycle of renewal. As we continue to explore the implications of the JWST findings, it is essential to remain open-minded and consider the broader context of our knowledge. The history of science is filled with paradigm shifts that have transformed our understanding of the world. From the heliocentric model of the solar system to the theory of relativity, each major discovery challenges existing beliefs and opens new avenues of research. The JWST data may represent another such shift, forcing us to rethink our theories and develop new models that better explain the complexity of the universe in the coming years. As scientists analyze the JWST data and make other observations, we may discover further evidence that the expansion of the universe has ended. This will require interdisciplinary collaboration, as physicists, astronomers, and cosmologists work together to interpret the results and develop new theoretical frameworks. Technological advances, such as more powerful telescopes and more sophisticated simulations, will also play an important role in this process. Ultimately, the journey to understanding the universe is a testament to human curiosity and the desire to understand the fundamental nature of reality. JWST's discoveries remind us that the universe is full of surprises, and that each new discovery brings us closer to unlocking the mysteries of existence. As we stand at the dawn of a new era in cosmology, we remember the words of famous physicist Richard Feynman. "I believe that the imagination of nature and of man is much greater than with human imagination. It will never let us relax." The journey to understanding the universe continues, and each discovery brings us closer to the ultimate truth. To better understand the impact of JWST's discoveries, we must delve into the intricate details of cosmological models and the fundamental forces that govern the universe. The standard model of cosmology, known as the lambda cold dark matter model, lambda CDM, is the dominant framework for understanding the structure and evolution of the universe. It integrates dark matter and dark energy to explain observable phenomena, notably the accelerating expansion of the universe. Dark matter, which makes up about 27% of the universe, does not emit, absorb, or reflect light, making it invisible to current detection methods. Its presence is inferred from its gravitational effects on visible matter, such as the rotational curves of galaxies and the gravitational lensing of light from distant objects. Dark energy, on the other hand, is an even more mysterious component, making up about 68% of the universe. It is thought to be responsible for the rapid expansion of the universe, acting as a repulsive force against gravity. The JWST observations challenge the lambda CDM model by suggesting that the expansion of the universe has slowed or stopped. This requires a reassessment of the role and properties of dark energy. One possibility is that dark energy is not a constant force but rather changes over time and space. This dynamic dark energy could exhibit different behaviors depending on the conditions of the universe, leading to periods of accelerating and decelerating expansion. The halting of expansion could also indicate the presence of additional forces or particles that we have yet to discover.